Hi guys, in the last video we were discussed few things. This is the one more video as a part of the quantum physics. In the last video we were discussed about the wave function and what are some properties. It's like both the momentum and position is uncertain. That means if you find the position, we cannot find the momentum. Similarly, vice versa also true. That is a recap of our slide. And let's go into the things. In this video, we'll discuss about some basic stuff which was required for the position and momentum. Then after we'll look into the Noether's theorem. Then we'll derive the momentum and the energy operators. There's a very important operators which generally we used in the any kind of manipulations. Like first, what does the operator mean? Uh, let's what operator do? Generally operator do like to manipulate the data to convert the state of one variable to another state. We need to do the operator operations like multiplication operation. If you do the multiplication operation, it will convert the state of one variable into another state. Similarly, we have the momentum operator and the energy operator. There's two are the most widely used operations on the quantum wave function. Okay, we will derive those two in this video. It's not going to be pretty hard. It's a very easy here to explain. Let's go into the video. Before that, we are going to be discuss some basic stuff which require to understand overall thing. Like if you want to find the expectation value of position, like how the uh, expectation value of your position or expectation value of moment, how we are going to find. That's we will see here. For that, we are going with a small example here. uh, Suppose in your class the people are there, couple of people with different ages, 14, 15, 19, 20, and the x-axis we consider as the ages and the y-axis we consider as the number of people with that age. To find the probability of if you pick a person, what's the probability of the person with certain age? For suppose if you want to find the, you pick a randomly, what's the probability of getting the person having age of 20? For that we just need to find the number of people with that age. Here is 5, and the total number of persons in the class, entire class, we have entire class 11, 5, 2, 3, 1. I have 11 people with different ages. Not some group of people with the same age. And if you want to find the expectation value of age here, how are we gonna find? We just take the ages of all the people by the total number of people. Like here we have 14 with one person, and the 15 3. Similar 19 with two people, and 20 is 5 folks are, and the total number of people is 11. You can see this just age, and this is the number of people. We we've written like this: numerator as n of a into a by the n total. Here we can say this probability is gonna be uh, we can use this equation to replace this part of the equation. Now expectation of a is we got in the probability. Similarly, if we have the function, then we can represent like this also. Now if we want to find the standard deviation of the function, we can also derive what's the use of the standard deviation. Why you're discussing the expectation, the standard. If you know the expectation and the standard deviation, then you know a lot of things about the system, like property. Similarly, if you know the momentum, expectation momentum, or expectation position, and this deviation of the position, then you know the lot of things about that one. Now let's apply if it is a continuous variable. In previously we have a discrete variable. Now if we are continuous variable, we need to use the integration. Integration is a beautiful property we have. uh, that awesome, I think. And we can just replace that with the integration and we will get the whole. See, similarly for the function, we just replacing with the integration. Still always okay, we find what's the use of it. We are using now to find the expectation value of position and expectation value of momentum. The values we are going to be find, we are going to be expectation values. Okay, like what we how why we need this one generally. If we are finding the probabilities. Okay, probability of position and but actually the probability what we are finding, it's not entirely correct. It's it's closer to the actual value. Okay, for that to avoid that deviation, to avoid that all the stuff, what we are doing a lot of time the same experiment. We are going to be repeat this experiment, then we will get lot of probability values. Okay, now by using those lot of probability values, we are going to find the average is position value. Average position, that's is very useful. You are more confident about the average instead of the single value. That's the reason expectation values are very important in the quantum physics. The expectation value of the position, we know the probability is a p of x, we can replace with psi of x. And similarly momentum, for the momentum we need to find the Fourier transformation of the position. When the Fourier transform, I will get this one, we just replace that one. Now we have the we just find the momentum and the position uh, values, like exact values. Okay, by doing a lot of time this experiment. Now let's look into the Noether's theorem. This is one of the most important theorem in the physics. Here you can see this symmetry is the one side and the conservation and this lot of stuff, translation, rotation, time, and the symmetry side and the conservation, momentum, angular momentum, the energy. Listen guys, it's a mesmerizing thing. It's very hard to understand the another stream, but if you apply the practical, you can get those things very easily. For the translation symmetry is gonna be conservation the momentum, and the rotation symmetry is conservation the angular momentum. The time conservation is time symmetry is conservation in the energy. What it's telling, let's suppose take some example, and it's better to go with some example. uh, if a particle is there and it's moving with in a straight line, then energy of the particle is with the time is equal to of mv square dt. Here you can see mv square, sorry, uh, here the energy of the particle is independent of the time. Okay, if you change the constant change in the time, the energy remains constant generally. If you take uh, uh, let's suppose if you have 0 to 1 we have dt. If you change the limits like 1 to 2, then after mv square, you need to convert dt plus 1. Okay, uh, the energy of this one and energy of these two are same. Still these are symmetry, these are symmetry. Similarly, I will give same example with the translation. Let's consider this Earth is rotating around the sun. This here is this change in the position. This momentum is remains constant. The uh, Earth is rotating with constant momentum. Just telling, momentum is conservative to the Earth. This is one more example for the momentum. Now let's apply how we can useful this to understand the momentum operator and the energy operator. We can use these concepts. Let's go into the energy and momentum operators. We know that any wave function we can represent with some of the wave function, that's called superposition. We call in the quantum physics, and in the mass we call as the Fourier. Right? It's just Fourier equation 1 by 2 phi into dk psi of k I of k x inverse Fourier. Okay, now let's go into the mass bit of mass of this, but it's not very difficult. We saw this equation, inverse Fourier equation, this one, and we previously we have only the position is there. We just added the time also to this one. Now we got the psi of x comma t. Now if you do the integration to this equation, you will just get some constant plus e for ikx minus wt, because this is the same in the integration. I just consider as a constant, and we know the momentum equal to h bar by hk and E equal to h bar w. These two equations we already discussed. By these two equations we can tell the electron has both wave nature and the particle nature. Now we can use these two, and we just replace these values with the p and e. Now we will get c into e I by h px minus et. Now let's do differentiation. It's like partial differentiation with the time of this equation. We just get I by h bar e into psi of x comma t. We'll get same thing here, and we just get this only, and I h bar by dou t, and we just convert this to operator. We just cap it as an operator. Similarly, if you differentiate with x psi of x comma t, you will get I by h bar p of psi of x comma t. Just p, you will get h bar by I dou by dou x. From this, what you understand from the Northwest theorem, just relate that thing here. From Northwest theorem, here it is, and we are differentiating the time. That means time is conservative in the energy of the wave function. Similarly, the position is conservative to the momentum in the quantum wave function. This is we just related. We just interpreted. Sorry, folks. Yeah, this is all most important stuff we required from the Northwest theorem. How we can understand the operators in the terms of time and the position. Yeah, in the next video we are going to be discuss few more stuff about Schrodinger equation. We'll derive the Schrodinger equation in the next video. Thank you guys.